Today's video is going to be on something called differential rate laws, which is really the major thing in rate of reaction or reaction kinetics. Again, this is all rate of reaction. So this is a little bit of a weird reaction here. We have hemoglobin, which is in your blood, and carbon monoxide. So some kind of reaction here. I'm not sure what even is formed or even what the coefficients are, but it doesn't really make a difference for this. But we're trying to figure out what the rate is of this reaction. So again, the rate doesn't stay the same all the time. Okay, you can change things to increase or decrease the rate of the reaction. Remember, again, these particles have to collide. It's all based on these particles colliding, the reactants colliding. So if you increase concentration, increase temperature, things like that can make more collisions will cause the rate to increase. So we're going to write something what's called the rate law. So almost every time we do something, actually this would be the major thing here, we'll always write what's called the rate law or rate expression. Rate law or rate expression. Okay, so here's some data they'll give you. This is different than the data that you've seen before. So these are 6 different experiments. So here's experiment number 1, number 2, number 3, number 4, number 5, number 6. These are separate experiments that they've tried and measured the rate. So what they're doing is they're changing the molarity. This is molarity. Okay, so this is molarity. This is molarity. They're changing the molarity of the reactants and seeing what the rate of the reaction is. So for trial 1, they tried this molarity of hemoglobin, this molarity of carbon monoxide, and they measured the rate of the reaction. And this would have been over a certain period of time they measured this rate. Again, this is in moles per liter per second. So moles per liter per second. Change in molarity per second. What is the change in molarity per second? So these would be decreasing as the reaction goes. You'd be increasing the product. So that's trial 1. Trial 2, then notice they changed this concentration. They doubled this concentration and kept this concentration the same, and then looked at the rate. So trying to figure out how these things, changing these concentrations, affects the rate of this reaction. All right, so our rate law. Our rate law or rate expression, we write this. We write rate equals K. Okay, and K is called the rate constant. Okay, it's called the rate constant, which is the same for this reaction unless you change temperature. K will always be the same for this reaction unless you change temperature, but K is different for every other reaction. And if we change temperature, that changes K also. So rate constant times the concentration of the product, the reactants, hemoglobin, times the concentration of carbon monoxide. So molarity of this times molarity of this times rate constant equals that. Now these are going to be raised to a power. So we're going to have, we put an X and a Y. Those are raised to a power. That is called the order for each one. That's called the order. And you find that order by having some experimental data like this. You find the order. So let's find the order for each of these. So, and the order has nothing to do with the coefficients in the balanced equation. The order has nothing to do with the coefficients in the balanced equation. So here's how you go about that. We have to compare 2 different trials. Again, this is experiment 1, 2, 3, 4, 5, 6. So if we look here, they're not changing this concentration. This concentration is doubling. It's going up 2 times. So if the rate changes, it's not based on this. If this rate changes, which it did, it's based on this concentration changing. So changing this concentration does what to the rate? Well, we look over here. That is 2 times bigger also. So doubling this concentration doubles the rate of this reaction. This is staying consistent. So what we do is we say 2 to what power? 2 to what power equals 2? Well, 2 to the first power equals 2. This doubled, this doubled. Now, had this gone up 4 times, we'd say 2 to the second power equals 4. So that would be called a second order reaction. So we'll do one of those later. But this one would just be, since this only goes up 2 times, when that doubles, that means it is first order first order with regards to hemoglobin. Okay, now let's figure out what the order is with regards to carbon monoxide. This should have a bracket around it. So we got to find a different trial. We want a trial where this is staying consistent and this is changing. Well, right here, this is staying consistent. This is going up 3 times. So let's see what happens to the rate. Our rate goes 1.24 to 3.71, also 3 times. So again, this is first order. When they change the same, it is a first order. If this didn't change at all, if tripling this didn't change the rate, that would be 0 order. Okay, so you can have a 0 order. Usually it's 0 order, first order, second order. Sometimes we'll get some different ones, but most times it's that. So this reaction happens to be first order with regards to hemoglobin, first order with regards to carbon monoxide. So changing these concentrations affects the rate the same amount. If one of these was second order, that change in that concentration would affect the rate a lot more. We call this first order with regards to hemoglobin, first order with regards to carbon monoxide, second order overall. Okay, second order overall. All right. If we notice there's some blank spots in the table, we'll fill those in here in a little bit. There is one of those we could figure out right now. We could figure this one out right here. And the reason being, we know this is not changing. This concentration is not changing. This is going up 2 times. So doubling this concentration without changing this one should double this rate because it is first order with regards to this. So this is going to be, what is that, 7.42 moles per liter per second. Now, here to here, it's like 2.5. That's changing also. Hard to figure that out. But we can figure it out by using this. We can do a little math and figure out this rate by plugging in these things. Okay, same thing over here. We can figure out what this concentration is by plugging into this. So we'll do that. So next thing, let's figure out K and its units. So I'm going to plug in a trial that we know everything for. So we could plug in trial 1, 2, 3, or 4 in this case. I'll probably just use 1. So I'm going to put in this rate in there, this concentration, and this concentration. I'll plug those in and solve for our rate constant and show you how to get the labels for that. So I'm going to scroll up here a little bit. All right. So the rate that we have up there, look at my sheet here. The rate in that first trial was I'm going to write this a little higher, 0.619 is our rate. I'm going to put my labels on here, moles per liter per second. There's our rate. Equals, we're trying to find that K value, called the rate constant, times the concentration of hemoglobin, which was 2.21 moles per liter, times the concentration of carbon monoxide, and that is to the first power because it was first order. So remember that, and other ones will be second order, times the concentration of carbon monoxide, which is 1 mole per liter. So we need to multiply those, which is going to be 2.21, and divide this side. Okay, that's pretty easy. So we're going to end up taking 0.691 divided by 2.21. So that ends up being, that divided by that ends up being 0.280. Now let's figure out the label. Okay, figure out labels. So we have moles times moles, liters times liters. So this side is moles squared over liters squared. Again, that was molarity times molarity. Kind of weird that we have squared units of those. And we're dividing this by that. So that's the same thing as multiplying by the reciprocal. Same thing as multiplying by the reciprocal. So we're taking this, moles per liter per second, and we divided it by that. So multiplied by liters squared over moles squared. Let's cancel some stuff out. We got moles here and moles here, so this becomes a 1. Liters here, so this becomes a 1. So we're left with liters per mole per second. Liters per mole per second is our label. So finding the units of K is always an important thing. 0.280 liters per mole per second. I will give you some ways to figure that out. I will tell you that this rate, this K value Whenever it's a second order reaction, so when I say second order, it's first order and first order, second order overall, we add those together, it'll end up being like this. If this would have been a third order reaction, these would have had some square units on them. So we'll figure those out as we go along. This is your rate constant. That is your K value. That is your K. So 0.28 liters per mole per second. All right, let's fill in the missing values in the chart. I'm going to delete. So in experiment 5. So now we know we can plug into this. We can say rate equals our K, which was 0.28 liters per mole per second, times the concentration of hemoglobin to the first power, times the concentration of carbon monoxide to the first power. So we can plug it into this and solve for any of these three things. This is our K value, remember, that's our K right there. So experiment 5, in experiment 5, up there at the top, we're looking for the rate. So we're saying the rate equals 0.28 liters per mole per second times concentration of hemoglobin is 3.36 to the first power times the concentration of carbon monoxide is 2.40 to the first power. So multiplying those, our rate ends up being, I think it's 2.26. Okay, so our rate is always in molarity per second, or moles per liter per second. All right. Experiment 6 is also missing some stuff. Experiment 6. And this time it gives you a rate. So we're going to put the rate out front. 2.5 is your rate. 0.28 is our constant. It gives us the concentration of carbon monoxide. We're looking for the concentration of hemoglobin. So we're looking for hemoglobin's concentration, and it gives us carbon monoxide at 2 molar. So a little bit of algebra there. We get a concentration of hemoglobin for that trial of 4.46 molar. All right, I'll show you one more example of how to do this without a whole lot of math in it, but give me a second. All right, I'll show you just a couple more examples here of how to write the rate expression here. So here's our first one. There's our reaction. Okay, there's our reaction. So if we're writing this, we're trying to write the rate expression for this. So we would say, it's going to be rate equals K, concentration of A, concentration of B, and both of these would be to a certain power up there. So here's how we figure out those powers again, the order of the reaction. So this is the order with regards to A, order with regards to B. So you need some experimental data. Okay, experiment 1. Here's our rate. Here's our concentrations of our A and B. So if we look here, A is not changing right here. B is going up 2 times, doubling. And when that happens, it looks like our rate is also doubling. So that is a first order reaction. When the concentration doubled, the rate doubled. So it's first order with regards to B. Doubling B's concentration doubled the rate. So this can be first order with regards to B. Okay, now let's figure out the order with regards to A. So again, we find a trial where B's not changing, A is doubling, and our rate did not change. So doubling the concentration of A has no effect on the rate. That means that A is 0 order. It does not affect the it doesn't matter if you start with 100 molar, 0 or 0.5 molar, as long as you have some A there for the reaction to go. It doesn't matter. It doesn't affect how fast the reaction happens. So that is called 0 order. Remember, anything to the 0 power is just 1. So essentially, rate equals K times concentration of B to the first power. Okay, let me do one more of those. All right, same reaction. Same reaction there. Again, let's write our rate expression. So let's figure out, we can do this. B is not changing right here. A is going up 4 times. So from 0.1 molar to 0.4 molar. So in this experiment, A is 4 times more concentrated. So let's see what happened to our rate. 1.5 to 6.0 is also 4 times. So that tells me it is first order with regards to A. So we know A is first order. A is first order. Let's figure out B. Here's where A is not changing. B is going up 2 times. And our rate went from 6 times 10 to the third to 2.4 times 10 to the negative second. That is 4 times higher. This is 4 times bigger than that. So doubling this concentration, when this one didn't change, doubling this concentration caused that to go up 4 times. That means this is second order, because 2 to the second power equals 4. So it is first order with regards to A, second order with regards to B. First order, second order. So our rate expression would be this one. Rate equals K, concentration of A, concentration of B to the second power. So if we want to solve for this K value, I could plug in any of these values. I could put in 0.1 for A, 0.1 and square it for B, put in this rate out in front, and solve for my K. All right, have a good day.